Now you will agree that at least the first of these commutation relations look very complicated. Although, as I have already explained, most of the terms are going to vanish anyway. So it's not really as bad as it looks. And it's really not that difficult to remember this particular commutation relation despite the rather complicated appearance on the right hand side. What is actually quite interesting is that there are very familiar commutation relations lurking inside these relations. All you have to do to see that is carry out some simple identifications which will map these J mu nus to other more familiar operators. To see this, let us first talk about the commutation of two J's with specifically spatial indices, that is J1, 2 and let's say J2, 3. I times that. Now, according to our rule, we will have a bunch of etas with a bunch of j's, multiplying them. But etas are diagonal, as I keep on reminding you. So the only time you are going to get a non-zero eta is when an eta has both indices equal. Now, among the four indices here, the only equal ones are this and this, which are nu and rho in our language. So, remember, the non-zero term will be eta nu rho. So, 2, 2. So, the two inner ones go into eta, and the two outer ones go into j. So, j, 1, 3. I don't even have to look at the other terms because they will only have etas with two different indices, so they will all vanish. Now, eta 2, 2 of course is plus 1, and j1, 3 can also be written down as j31 with a minus sign, so you can write this as minus j31. So, we can write j12 and j23's commutator as I times j31, where all I have done is move this I to the other side. And 1 by I is minus I. We have just used that. Now, this one commutator may be enough of a hint for you to realize which particular familiar Lie algebra we are talking about here, or familiar set of commutators we are talking about here. But if that doesn't ring a bell, let's look at the next one. I, j23, comma, let's say j31. Once again, is the two near indices which are equal, so you will get eta 33, j21, which is minus j12, and we end up with j23, j31, is I, j12. And the third commutation relation that we can write down in this set, which is that of j31, j12. I'm pretty sure you can write this down without even working it out, or working it out in your head, eta 11 times j32 with a minus I, and that's really I times j23. Now, this set of three commutation relations should be very familiar to all of you, especially once you identify j12 with j3, j23. Okay, I wrote j12 with a lower index, but I've been writing it with an upper index so far. However, it doesn't really matter because if you lower two spatial indices, you do it with eta lower mu nu, and those will contribute plus 1, so there is no real difference. But still, for consistency, j23, let's identify that with j1, and the final one, j31, let's identify that with j2. Once you do that, you can easily see that this actually is nothing but the angular momentum commutation relation, a very familiar thing. Let's just make some space and write this down here. Let's say in red. Ji with jj is I epsilon ijk jk. Now for another identification which is pretty handy. J01, J02, J03, J's with one temporal and one spatial index are going to be identified with K1, K2, K3. I've already explained in a previous part of this lecture that these talk of infinitesimal transformations which mix time with one of the spatial indices. So these are basically Lorentz boosts. So what kind of commutation relations do Ji and Kj obey among each other? So let's try working one of them out. Let's say J1 with K1. Now J1 of course is J23 and K1 is J01. Now notice that all the four indices on display here are different. So each of these etas will have two indices which will differ. So you must get a 0. So J1 commutes with K1. What about J1's commutation with K2? That will give you J23 with J02. So now you have two outer indices which are equal. So they will go on an eta. So mu and sigma will go on an eta. That's the last term here. And J nu rho. So J30. With an extra minus I, which comes when you move the I on this side to the other side. So this gives you plus I times J03. So I times K3. What about J1 K3? That's J23's commutator with J03. So you get a minus I times whatever you get from the commutator on the right hand side. Note the 3 and 3, these two indices are equal. So if you go back here, you're essentially saying you want nu and sigma to be on eta, which is this term. So minus eta nu sigma J mu rho. So minus J20. So what you get is I times J20, which is minus I times K2. At this stage, it should be possible for you to guess that the commutator between Ji and Kj will work out to be I epsilon ijk times Kk. Now, you can easily check on a case-by-case basis using different values of I and j that this is really correct. Of course, I've already checked the case for I equal to 1, but you can also extend this to other cases as well. But it would be nice if we could actually prove this algebraically in one go. And we can do that. But for that, what we need to do is we need to take a look at this identification and write this in a bit more compact manner. So one easy compact way of writing this identification is simply this. If I wrote Jij equals epsilon ijk, capital J small k, you should be able to check that this captures these identifications exactly. For example, if I take J12, on this side you will get epsilon 1 to k jk, and the only value of k for which epsilon 1 to k is non-zero is k equal to 3. So you'll get epsilon 1 to 3 j3, that's plus 1 times j3, and hence j3. And you can easily check that the other two also works. However, what we will need is actually not this, but its inverse, so to speak, that I need to be able to write Ji with a single index, the angular momentum component, in terms of these double index capital J's. Now, if you were to guess that the answer is epsilon I jk times capital J jk, you would be almost right, but not quite. Just to see that, okay, first let me get rid of these workings on this side to make space for what I want to write down now. just as I said, to check, J1 would be epsilon 1 jk jjk. Now with I equal to 1, there are exactly two choices for j and k for which this epsilon 1 jk is non-zero. One is j equal to 2, k equal to 3. The other is j equal to 3, k equals 2. So basically this term will be epsilon 1, 2, 3, j 2, 3 plus epsilon 1, 3, 2, j 3, 2. Now it is easy to see that this term is exactly the same as this term. J32 is minus J23, but epsilon 132 is minus 1 as opposed to epsilon 123, which is plus 1. So what you will get when you add them together is J23 with an extra factor of 2. Now you don't really want this extra factor of 2, and the way out is simple. You have to put in a half here. So the formula that we are looking for is Ji is half epsilon ijk jjk. Now using this and the fact that ki is j0i, let us verify the expression for ji commutator with kj. For this, once again, let's get rid of this extra working. And let's try calculating the commutator algebraically. So we are going to try calculating Ji's commutator with Kj and essentially end up proving this result hopefully. So Ji is, as we have just written down, half epsilon I, but now I cannot write Jk, capital Jjk, because I don't want to confuse with this J. So I will write epsilon I KL J KL with J0J. So it's half epsilon IKL JKL's commutator with J0J. Once again, you should expect 4 terms with 4 etas, but the only non-zero etas will be ones on which the two indices match. Now it is possible for k and j to match and l and j to match, but the other possibility that k will match 0 or l which will match 0 is simply out, because KL here are spatial indices, they can never be 0. So we have two non-zero terms here. One, when I get k with j, that's the first with the last. So eta mu sigma, the last term here, which has j new row with it. So that's going to be eta kj with j L0, and the other term will be the one where you get L with j, so that's mu with sigma, this term. So with a minus sign here, so eta Lj and mu with rho, so K0. In addition to all this, there is a factor of minus I which you get when you move the I to the other side. So this becomes minus I by 2 epsilon I KL, and this further simplifies because eta kj after all is delta kj j L0, or I could simplify this to k minus KL anyway directly, plus delta Lj capital K small k. The plus sign comes because of the minus sign which you get from jk0 being minus capital Kk. So now let's put them together. You get two terms, I by 2, epsilon I, because of this delta kj it becomes epsilon I jl kl, and this term becomes minus I by 2 epsilon I kj kk. it's very easy to check that both of these two terms are equal, epsilon ikj being minus epsilon ijk. Of course, I can write this as epsilon ijk. So, putting them together, I do get I times epsilon ijk. So, this is verified. In exactly the same way, and using the commutation relations between P rho and J mu nu, you can establish this result, which I'm just writing down and leaving as an exercise for you. Ji's commutator with Pj is I epsilon ijk pk. Now, in case you have not noticed so far, let me point out that these three commutation relations are very, very similar. You have commutators of Ji with the small jth component of something, and on the other side you have I epsilon ijk times the small kth component of that thing in each of the three cases. So they, in a sense, they are identical commutation relations. And that should not come as a surprise to anybody who has done a bit of advanced quantum mechanics, where you learn the connection between rotations and angular momentum. After all, these three sets J1, J23, J31, J12, which is of course nothing but our J1, J2, J3, J01, J02, J03, which of course is nothing but our K1, K2, K3, and finally P1, P2, P3, the three spatial parts of the four vector capital P mu, P lower 1, P lower 2, P lower 3. They all are examples of what are called vector operators. Now, capital J, the thing that you're commuting them with, generates rotations. And under rotations, all vectors change in an identical manner. And that's exactly why the commutator of J's with any vector operator would give you exactly this kind of a commutation relation. So these commutation relations are just a sign that these objects, the 3 J's, the 3 K's and the 3 P's, are vector valued operators. Now, in addition to these commutation relations, you have commutation relations like Ki's commutation relation with Kj. How would you figure that out? So let me just get rid of the clutter on this side, and then we are going to work this out. What we want are these commutators, Ki with Kj. But Ki Kj is of course J0i with J0j. And now comes the question of choosing the right indices to put on the etas. Now there are two ways in which you can get non-zero etas here. One is take 0 with the 0 and put that on eta. Of course, taking 0 with the 0 is equivalent to taking mu with the rho, which is this term. So you get, apart from a minus I, you get minus eta 0, 0 and Jij. Of course, the other way in which you could have put the same index on eta is if you put I and j on eta, and then of course you will get a non-zero value if I were equal to j. But if you were to put I and j on eta, the capital J will get indices 0 and 0, and that would of course vanish. So you have only this 1 0 term. So what you get here is I times eta 0, 0 times jij. So this is actually minus I, the minus coming because of the fact that eta 0, 0 is minus 1, and jij you can of course write as epsilon ijk jk. So our commutation relation, the one we wanted to work out, is given by this. Before we go on to talk about the next commutation relation in the list, let me quickly point out that significance of this particular commutation relation that we have derived just now. This may be a bit unfamiliar to many of you. And notice that what it is telling us is that if you have two boost generators in different directions with different I and j, the commutator is actually a generator of rotations. Now, what this means is rather fascinating and complex. And there's every chance that in trying to describe this, I might go overboard and spend way too much time on this. So I will try to keep this very, very brief. The basic idea is the following. If you consider two different boosts, one from the observer O to the observer O prime along U, and another boost from O prime to O double prime with a velocity v vector, the result is not really just a boost. Remember, a boost is a Lorentz transformation where the axes stay parallel to each other. So the axis of O prime are parallel to the axis of O. The axis of O double prime are parallel to the axis of O prime. So it seems like the axis of O double prime must stay parallel to the axis of O. And hence, this transformation which takes you directly from O to O double prime, the composition of the two Lorentz transformations that we have carried out now, must really be a boost. However, that's not quite true. When you say axis systems are parallel, you actually mean that if you looked at two ends of an axis vector at the same instant, you would find it parallel to your axis vector. So there is a notion of simultaneity involved here, and simultaneity is relative, let me point out. And as a consequence, what happens is that the result of two boosts in two non-collinear directions happens to be not just a boost. Two boosts in the same direction gives you a boost. That's something which you are familiar with, and that gives rise to a familiar velocity addition formula. However, if you were to delve a bit deeper and look at velocity addition formula for non-collinear boosts, where u and v are not in the same direction, you will find that u plus v is not the same as v plus u. This non-commutativity actually tells you that the velocity of O with respect to O double prime and the velocity of O double prime with respect to O are not negatives of each other, which goes against a very basic principle which has been carried over from classical physics onto Einsteinian physics. It's called the velocity reciprocity principle, and all that it really means is that if the velocity of one observer with respect to another is u, the velocity of the first observer with respect to the second must be minus u. Apparently that's violated here, but it's really not. The point is, you will find that the two resulting velocities have the same magnitude, they just don't have components which are negatives of each other. And the reason behind this is, when you compose two boosts, you just don't get a boost, you also get a rotation. And it is this rotation which is actually being generated by the right hand side of the commutator here. Now this additional rotation which comes in whenever you have boosts in non-collinear directions, it's called Wigner rotation or Thomas rotation, or sometimes Wigner-Thomas rotation. This is related to another phenomenon which many of you may have already heard about, called the Thomas precession, but it's not really exactly the same phenomenon. But this particular commutator essentially is telling you that two boosts don't really add up to a boost, they add up to a boost plus an additional rotation. Now let us go on to our next commutation relation on the list. What about Ki with Pj? Now let's try working that out again here. Ki with Pj would be J0i with P upper j. So that will be actually minus Pj with J0i. I am doing that simply to ensure that we have the same form as the commutator written here. So what this gives us is plus I, minus I and a minus 1 together, times the one term which can give you a non-zero eta, that's where you put j and I on eta, so giving you eta ji. That's the second term here. So that minus eta ji is the same as delta ij, and then p0. So what you get is minus I delta ij times p0, which is of course the Hamiltonian. This is the first time we meet the Hamiltonian p0 in our discussion. The next step, of course, would be then to find out commutators of the H with the various sets that we have talked about. Now, it is very easy to figure this out, and I'm leaving that as an exercise for all of you, that Ji actually commutes with H. Not only that, Pi, the spatial components of the 4-vector P, of course commutes with the temporal component, because all components of P mu commute with all components. And H, of course, commutes with itself. No prizes for guessing that. The only commutator left out at this stage is that of Ki with H. So let's work that out again. Ki with H is J0i with P0, or minus P0 with J0i. Now 0 can never be equal to I, but 0 of course can be equal to 0. So you get plus I, that's minus times minus I of course again, times eta 0, 0 times Pi. But eta 0, 0, remember, is minus 1, so this is minus I Pi. So our final commutation relation is, we could either work with this set of 3 commutation relations. These are really 3 sets of commutation relations between J's and J's, P's and J's, and P's and P's. Or you could work with this larger number of commutation relations involving mostly operators which are more familiar, like the angular momentum, the momentum, and the Hamiltonian. Of course, you have to include the boost generators which are not familiar, at least not familiar from non-relativistic quantum mechanics, but they also have reasonably simple commutation relations. Both the ways of looking at these commutation relations for the Poincare algebra are fruitful, and you need to be able to sort of talk in both languages, so to speak. Now, during our general discussion on continuous groups, we have seen 2 special cases where we can actually find out the expressions for group elements or their corresponding unitary operators even when the parameters are not infinitesimal. And that is when you have an additive group, or a group where the parameters add on composition. This also works for subgroups of any group that you have. In the Poincare group, there is one very obvious example of such a subgroup, which is basically this. If you take 2 Poincare transformations, which are just pure translations, then either from the Poincare group composition rule or simply from the definition of translations, it should be easy to see that these 2 successive translations actually give you a single translation given by the translation parameter a bar plus a. So this, of course, is obviously an additive situation. So for this, the corresponding unitary operator acting on the Hilbert space ui, a will simply be given by exponential of minus I p mu a mu. Just to remind you of how this works, basically, because of this additivity, you can talk of this as breaking this whole thing up into n parts. So, a mu by n will be the parameter which will become infinitesimally small for huge n. So, 1 plus minus, because that's what you have with n, minus I, a mu by n, p mu to the power n, which is exactly this exponential. So that's one case where you can easily figure out the corresponding operator for a finite transformation. There is another case when you actually rotate about a given axis through an angle theta. So if you carry out a Lorentz transformation, which is just a rotation, and do not translate at all, you are going to get this particular operator, which, by the way, again gives you additive parameterization, because if you rotate through theta bar, after you rotate through theta about the same axis, the overall thing is a theta plus theta bar rotation through that axis. And using exactly the same kind of arguments, you will land up with this particular and rather familiar form for the unitary operator corresponding to this rotation. So these are the two special cases which are going to come in very handy when we talk about the action of Poincare group elements on states in the Hilbert space, something we will do pretty soon.